COVID-19 rat kits and pregnancy tests. We've all heard of them. But what do these two things have in common? Well, they both use special immune proteins called antibodies to detect the presence of a particular substance known as an antigen. In the case of COVID-19 rapid antigen tests, antigens are typically armed against the spike proteins found on the surface of the viral particle. And for pregnancy tests, antibodies detect a hormone released in the placenta during the early stages of pregnancy. Now, some of you might be familiar with traditional monoclonal antibodies, but more recent technologies have seen the adoption of a new generation of antibodies known as nanobodies. So how exactly do these nanobodies differ from the traditional antibodies? Well, it all starts inside the body of camelids, like alpacas, llamas, and camels, where antibodies used in research and therapeutics are typically produced in mouse or rabbit cells that are hybridized with cancer cells. Nanobodies are derived from special antibodies found in these camelids called heavy chain antibodies, or HCABs for short. If we compare the structure of these HCABs to our traditional IgG, they look pretty similar, both sporting a constant fragment stem and variable fragment arms. But if we take a closer look at the variable fragment, we can see some pretty big differences. HCABs have a variable fragment that only consists of a heavy chain, unlike IgG, which has both the heavy and light chains. We can also see that the variable region on HCABs only has a singular domain, leaving the job of antigen recognition to this part alone. This means that scientists can rapidly and inexpensively express the small HCAB variable fragment on its own in bacterial cells to produce camelid-derived antibody fragments that have not so creatively been termed nanobodies. Using this method, they don't even need to sacrifice animals. They simply immunize alpaca with the antigen and take small samples of their blood after they start making HCABs against the antigen. So we can grab the DNA that codes for the HCAB, cut out the nanobody part, and stick it into bacterial cells so they can start pumping them out like a little protein factory. And since HCAB antigen recognition only requires this nanobody section, they can still bind to that antigen. The most interesting thing about nanobodies is how they bind to that antigen. Let's have a quick refresher on how antibody specificity works. You can think of antibodies binding to the antigen partner as kind of like ice cream preferences. Now hear me out. Some people like chocolate, some people like vanilla, some people like mango, and some people like toothpaste. Sorry, mint. These ice creams are our antigens. We are the antibodies. So what determines our preference? Our tongues. If we zoom in even further into the variable region of both IgG and HCABs, we can see something known as the complementary determining regions, or CDRs. These are subdivided into 3 CDRs, which together form the antigen binding site, which we can think of as a tongue that gives rise to our ice cream preferences. The structure of these CDRs are relatively similar between HCABs and IgG, but we can see that HCABs have an extended CDR3 loop that resembles an extra long finger. Now you might be thinking, why does this matter? Well, picture this. Homer's been at work all day and has worked up an appetite. So he heads on over to the vending machine and chooses his favorite candy bar, sticks his money in, and waits for it to drop. But disaster strikes, gets stuck inside. Homer is not impressed, and decides to test his luck and reaches in to grab it, but his hands are too girthy and his fingers are too short to reach. But luckily for Homer, it was bring your daughter to work day at the nuclear factory he works at. So he recruits Lisa's help, and she manages to get it out. Her smaller hands and longer fingers were able to just reach in and push the candy bar out. Good job, Lisa. So now that I've satisfied my craving for snack-based analogies, we can start to think of nanobodies like little hands. Nanobodies with their small size and extra long finger-like extension allow it to access the nooks and crannies of the antigen that are normally too hard to reach by the big and bulky human IgG. Scientists all around the world have begun to embrace the ingenuity of these nanobodies and are researching how they can use them to make new diagnostic tests and therapeutics. For example, chimeric nanobodies conjugated to the constant region of human IgG can be used to make new rat tests for norovirus. And the same technology has been used in our ongoing battle against SARS-CoV-2, and some evidence has even shown it has the potential to be a novel therapeutic.